Hi there. In this video I'm looking at a little bit of GCSE further maths and we're going to start off with matrices. So matrices is going to be something you've probably never seen before. So the first thing we're going to look at is what is a matrix. So this is quite a tricky question to answer because there's lots of different interpretations of what a matrix is and what its applications are and how it can be used. I suppose the simplest definition is it's just a grid or an array of numbers. So for an example, 1, 2, 3, 4, 5, 6. That is a matrix. Generally speaking, column vectors, so the column vector 2, 3, that can be seen as a matrix. A matrix could just be a single number, and that, if we're looking at matrices, can be considered a matrix. So there's lots of different things matrices can, lots of different forms matrices can take in terms of shapes and sizes, but generally speaking, it is just a grid of numbers. Now the numbers can be 0, so that's still a matrix. The numbers can be negative, so that's still a matrix. The numbers can be fractions, they can be rational, 2/3, or they can even be irrational. These are all still matrices. Okay, so just look at a little bit of nomenclature around matrices and specifically how we define the size of a matrix. So if we want to describe the dimension of a matrix, well, the dimensions of a matrix are just its size, and they're always written height by width. So the dimension of this matrix, well, the height, it's 2 numbers tall, and the width is 3 numbers tall, or 3 numbers wide, I should say. So the dimension of this matrix is 2 by 3. And the dimension of this matrix, well, it's 2 numbers high, and the width is 1. So that's a 2 by 1 matrix. And then this last one, I suppose, is the most simple. That's just a 1 by 1 matrix. Okay, there are also some special matrices we need to know, or special families of matrices. So if the dimensions if both the numbers are the same, then it's called a square matrix. And that kind of makes sense, right? A 2 by 2 matrix, that's a square matrix. A 3 by 3, a 4 by 4, any matrix that's a square is a square matrix. And then in these square matrices, we've also got 2 special matrices that we need to know. There's the 0 matrix. This one's quite easy to guess what it looks like. So the 2 by 2 0 matrix is just a grid with zeros in it. So that's the 2 by 2 0 matrix. I'll let you guess what the 3 by 3 0 matrix looks like. So then the 0 matrix, and we've also got in the square matrices identity matrix. Okay, now this word identity is an interesting one, and it's something we'll certainly explore much more in depth in later videos, but the main takeaway from this is if you see the identity matrix written down, it's leading diagonal, so going from the top left to the bottom right, they're all 1s, and the rest of the entries are 0s. So the 2 by 2 identity matrix is this. Could do a bigger identity matrix if we did a 4 by 4 identity matrix, exactly the same. 1, 2, 3, 4. The lead and diagonal are all 1s, and then all the other numbers are 0. So again, in later videos, we'll have a look at exactly why we call this the identity matrix and the significance of that. But just for now, this is sort of an overview of what a matrix is. And again, we'll look at sort of what they represent physically in the next video. So certainly when I was starting to learn about matrices, one of the hardest things I thought, to wrap my head around was actually how to visualize these matrices. Now, as you go further and further and further into your maths career, you'll start to realize that nice visualizations can often be a little bit misleading, and we can't rely on those wholly. They need to go with some sort of formalization. But certainly to start with, one of the best ways that I found to visualize what a matrix is almost as a collection of vectors. Now, this doesn't always work, and it's certainly not true for all applications of matrices, but when we're thinking about the transformations that we'll be looking at GCSE Maths and GCSE Further Maths, certainly initially thinking of them as collections of vectors is a good starting point. Because remember, a vector, 3, 4, that just means we go 3 to the right and 4 up. But if we've got a situation where we need to remember several vectors or several, if they're position vectors, several coordinates, then we can form a matrix out of, let's say, 3 vectors, for example. So this matrix is made of the vectors 1, 2, 3, 2, and 3, 4. And that might represent something like the vector 1, 2 is here, the vector 3, 2 is here, and the vector 3, 4 is here. So you can almost think of that as some sort of encoding of this triangle, particularly if these are all position vectors measured from the origin. And this has a really nice consequence in that if we can think of matrices as collections of vectors, we can also start to think of these matrices, and one of the main ways we can think of matrices is as transformations. And let me explain why that works. So this matrix 3, 4, this vector, 3, 4, well, it's 3 lots of this little vector to the right, which we call I hat, and it's 4 lots of this vector going up called j hat. Okay, and if we do a transformation on this vector, let's say we rotate it 90 degrees or we enlarge it scale factor 3, it turns out, and we'll explore this more in the next video, that all we need to remember, all we need to keep track of, are where this little vector 1, 0 ends up, and where this little vector 0, 1 ends up. So let's, just for sake of argument, pretend that we've done a transformation, and this I hat ends up here at, let's say, 3, 2, and j hat ends up here, let's say minus 4, 5. It turns out that if we write our matrix as where I hat lands, and this little dash here means the image of I hat, so where it lands, so 3, 2 as our first entry, or as our first vector in this matrix, and our second entry is negative 4, 5, where j lands, then this is enough to encode this transformation for any vector. We can use this matrix to transform this vector 3, 4 if we want to. So in terms of visualising matrices, a really rudimentary way we can visualise them is just as a collection of vectors. That falls down fairly quickly without a little bit of rigour, but certainly a more rigorous way we can visualise these, particularly if we've got a square 2 by 2 matrix or a square 3 by 3 matrix, is as a representation of a transformation. So again, in our next video we'll look at matrices as transformations in a little bit more depth, sort of seeing what they represent and why they work. But yeah, it's one of those things that you'll eventually, once you've used them a little bit more, and become a little bit more familiar with, you'll get used to the idea of what they are. Okay, good. Okay, so this is a little bonus bit of the video. You don't really need this for GCSE Further Maths, and even if you go to do A-level Further Maths, you only really need this if you do decision maths, and particularly decision, sort of the second unit of decision maths. because we don't really see this until then. But I think it would be remiss of me not to sort of point out this really other quite nice representation of what these matrices are and another application of them. So we've got a network here, or a graph is the other way it's called it, and we can think of this as like a map on Google Maps. So we've got 4 towns, A, B, C and D, and we've got a few roads that connects them. This is a bridge here, so those roads, it's not a junction, one goes over the other one. And we can use matrices to sort of represent this graph in sort of a more numeric, more computationally friendly way, which we can do a lot of stuff with. So we can think of this as A, B, C, D, A, B, C, D. So we can think, is there a road connecting A and B? If there is, we'll write a 1. And if there isn't, we'll write a 0. But there is a road connecting A to B, A to C and A to D, so they're all runs. There's a couple of ways we can think about this A to A. We can either say there's no road connecting A to A because A is at A, so we write it as a 0. We can say, well, if we're at A, we can get to A by just staying still, so we can encode it as 1, or we can just leave it blank. For this example, I just encode it as 1, but again, different applications have different conventions there. So then, is there a road connecting B to A? Well, yes, B obviously connects to B. There's not a road connecting B to C, but there is a road connecting B to D. Similarly, C only connects to A and nothing else, or C I suppose also connects to C, doesn't it? And then D connects to A, B and D, but not C. So this encodes information about where we can go to. And it turns out that encoding like this, things like matrix multiplication and other aspects work really well. There's lots of things we can do, lots of things we can work out. The other way we could encode information is if each of these has a length or a weight attached to it. So you can almost imagine them like lengths of roads or average time to drive along a road. Then in this matrix we can encode the shortest distance it takes to get from A to each of these points and from B to each of these points. And the really nice thing about that is if one of these is a one-way system, we can still encode that information on the matrix. Okay, so things like Google Maps and other sort of map software and Google searches, if these are all websites, and so the number of times there's a reference between them, a link from one website to another. It's the sort of thing that Google uses all the time to crunch in these really big matrices to sort of figure out what's the shortest route you can take to get from your house to school, or which website is most relevant to this other website you've looked at, along with various other things. But yeah, I think I would really be remiss to do this whole video series without talking at least a little bit about graph theory and how matrices relate to that.